offset for level I equals I plus 1. So I plus 1 equals the max cells. And then we just add level offset. And this is at the bottom level, so we know the bottom level is, 3. Okay, so this is how we accumulate the multiple expansion. Okay, so we are now done with P to M. Now we need to do the M to M. And we need to apply the same logic to these P's and I's. So right here, we just note P and I, but these need to have that level offset as well, because otherwise there's a cell number 0 at every level. So cell 0 at level 3 is here, but then if you go up a level, this whole cell is called cell 0 again. And so if you access the multiple expansion with that number, it would look like you're accessing the same index, but at different levels. It means a different box. So when you're calculating this thing here, this is not actually P and I. It's actually P plus the level offset at the parent level, and I plus the level offset at your current level. So you need to add those two things here. But that's about the only thing you need to change. So let's make it clear what we are calculating here. So here, this loop here is the P to M kernel. And then the next operation here, so it's not a very long code. Each of these P to M, M to M, L to L, and L to P parts will probably be like 5 or 6 lines of code. So in the M to M part, we will actually have to loop through the levels and then through the cells at each level. So maybe I need to define another integer here, like L for the level, because there will be 3 loops. So level, I'm going to loop backwards because I want to start from the bottom level, which is 3, and then I want to go up until it reaches like level 0 maybe. And L, it needs to be decreasing. Okay? So at every level, I want to access my multiple expansions of each cell. So now let's have a loop over the cells. Every time it starts from 0 and goes to what? The number of cells at each level, which is like what would this be? The level offset difference? Oh, it's actually this thing here. Cells per level. What should I? Yeah, let's just write here NC. So this is a number of cells per level. So if in case you don't understand what this is 2 to the power of 2i, which means it's like 4 to the power of I, which is the number of boxes in each level, right? Because I is the level. Sorry, this should be L. So this is 4 to the Lth power, which is the number of cells at each level. Okay, so I'm looping over all the cells by doing this. I'm looping over all the levels, bottom up, from the bottom level to the highest level 0, and then I'm looping over all the cells at each level. So when L is 3, this will be 2 to the power of 6, or 4 to the power of 3, which is the number of cells it would be 64, the number of boxes at level 3. And when this is 2, this would be 16. When this is 1, it would be 4. And when it's 0, it's obviously 1. So we are looping over all the cells at each level by doing this. And now for each cell, we calculate, okay, so maybe this shouldn't go all the way to level 0, because what this loop does is it first finds its parent, and for level 0 there is no parent, so we shouldn't go to level 0. So to find the parent, what is the index of the parent? So the index of the parent is the current index divided by 4. Right, and this current index doesn't have the level offset, so it's just dividing by 4 will give you the parent index without the level offset. So what we need is to add this level offset so that when we calculate so the level of the parent, this should be -1. Because we're looking at 1 level up. So the level offset should be for the level 1 level up. Okay, so this is the index of the parent. So multiple can be indexed. Why don't we, this is long, so let's just call it IP. This multiple is accumulated. This is the parent multiple. Now, where do we accumulate from? So now we have to access the multiple of the child cell, which is I plus the level offset of the current level, right? Because so when I mentioned earlier that we need the level offset, it's because right now this I is exactly this I, and this P is sort of this P, but we've already added the level offset to the IP. And yeah, so now we are adding level offset to both this side, and then this side has already been added here. So I divided by 4 will give you the not offsetted Morton index, and then we use the level offset to give you the exact index for the multiple. This way, the number here that's accessed in the multiple array will be different for each level, even if it's like 0 and 0 at 2 levels. If we're looking at the corner boxes at 2 levels, they can both have index I equals 0 and I divided by 4 equals 0, but multiple will be added the level offset of the parent level, and this will be added the level offset of the current level. So you will be looking at, inside the multiple array, you'll be looking at the correct locations, just so you are aware of the multiple being stored at different levels. Okay, so now this M2M, this is all. We're finished with the M2M. Okay, now we can either go on and finish the L2L and the L2P, or if we want to do things in order, here becomes the difficult part of calculating the M2L kernel. So yeah, maybe we should do the M2L kernel. Yeah, okay. Because it would be good if we can finish a proper FMM code today. we have a little bit more time, but let's see if we can finish up to the L2P, all the kernels. Okay, so now comes the M2L kernel. So the logic is quite similar to the M2M in the sense that we have to loop over all the levels, but now we can go from up to down because we have everything we need in all the levels. We just need to make sure that, and the good thing is, these are the only levels we need to look at. The reason is, at level 0, maybe I should show you a picture. At level 0, there's only one box, so M2L does not happen. Yeah, this picture is a very good picture. So this is the picture for level 2. Okay, this is already level 2. Level 0 is the whole box, just one box. So, and level 1, everything is a neighbor. So there's no M2L, there's no far red and blue boxes, as I explained yesterday. So we start from level 2 and then go down. But right now we only have level 3, so we just do these two, basically. Level 2 and level 3. This is what the picture of level 3 looks like. And we just need to do this calculation at level 2 and this calculation at level 3. We need to find, first, loop over all the blue boxes. So we loop over all the boxes and pretend that those are the blue boxes and try to find the red boxes for all of those blue boxes that we're looping over. So it's 2 loops. One for the blue box that covers all the whole domain, and then the loop that finds the red box, which consists of doing this calculation here. So let's see if we can do this without too many too much unnecessary code. So let's first loop over. So we know how to loop over all the boxes in a given level. We did this here. Oh, what happened? So we did this here, and so we know how to loop over. So this is the same logic, right? We know how many cells there are per level, so we just loop over that number, NC, number of cells per level. Okay, now we are looping over all the blue, the picture is not here, but so this loop is the loop for the blue boxes at both levels, right? First, we're looking at level 2 and looping over all the blue boxes in this from I equals 0 to I less than NC. This is the loop for the blue boxes. Okay, now each of these I's is the Morton index, right? Because we're assuming that we're just looping over the Morton index at all of these levels. Okay, now given this Morton index, we need to do, what was it? The get IX. And we've confirmed that if we put here 26, it gives back the correct answer. We did this here. So get IX. So let's take this whole part. We're going to copy this whole part here. All of this, and use it here. That's why we did this in the beginning. We did this test with 26, and we know it works. Now we are going to do the same thing for not just 26, but all the boxes, and for all the levels. Well, not all the levels, just levels 2 and 3. But we are going to do the same calculations. We know that this. Oh, I don't need to define IZ. We know that this works for 26, and we've confirmed that this actually returns in this index IC all the neighbor box indices. So oh wait, that reminds me, I think, yeah, for now it doesn't make any difference because it's safe to assume that So in the actual case where Q is not 1 everywhere, we need to be a little more careful between the difference of I and the actual Morton index. We need to use the Morton index instead of just I. But now it's fine because it's 1 anyway. And that will make a difference when you, because again, we're assuming here that this I is the Morton index. In reality, we have calculated the Morton index in the beginning at level 3. We know what it is. So it's this, we need to use this thing. This index is the actual Morton index. We need to reference that. But for now it's okay because it's 1 everywhere. So it's safe to assume that the multiple expansions calculated here are, no, but maybe it's not okay. I think we still need to calculate the proper Morton index we need to change this I here to the index I, because it changes the number of bodies in that cell. So the part we need to change is here. So this needs to be index I. Okay, then what happens is instead of accessing just any index in the from 0 to n cells, it's actually looking at the index that corresponds to this offset, I think. Right? No, wait. No, sorry. This is not right. This index is the index of each body. So it should be more like this, I think. Right? So this index will return the Morton index of given a body J, and J is the index of each of the bodies. So if we have this one here, it will accumulate in the proper multiple expansion. So this I here will give you the correct location of the multiple. Okay. So now, I think even for these two, now we can assume that this is the Morton index. This I is the Morton index. And here we are also assuming that this I is the Morton index. And this IC is the Morton index of the neighbors we are calculating. Okay, so now that we have the indices of both, we need to access the multiple expansions. And we need to do the same thing. So we haven't allocated the local expansions yet. We need to do the same thing we did for the multiples here. Local expansion. So for now, this is you can think of this as identical to UI. because we're assuming that ui prime and ui are the same in this whole calculation. And these are like qj primes. But we're calling them multiple because, as I've mentioned in yesterday's slides, this is the concept of the multiple expansion, the 0th order multiple expansion. And so I'm going to call them multiples. And these I'm going to call local expansions, the things we will calculate with the Q over R of the multiple expansions. Okay, so basically what we have now, oh wait, this is just, what do we have here? We just have the neighbors, right? We have the neighbors. Okay, so no, this is just the neighbor finding. I don't want to find the neighbors. I want to find the parents' neighbors. So I need to find, the parents' neighbors. And this will give me all the parents' neighbors. Okay. So IC here are the parents' neighbors. Now I have all the parents' neighbors here. And now I need to look at the children of my parents' neighbors. Oh, there's one more thing. So in the case that we were looking at before, so here, we knew that we were calculating for 26, so we had all the neighbors. So, but what if we are calculating for 0? On this side, we won't have any neighbors. So this calculation will return something strange if we don't account for that. So say this -1, looping from -1 to 1, -1 to 1, will do something strange if it's at the corner. So we need to consider the corner case. And that's actually very easy, because all we need to do is make sure that this ix2, that's the index of the neighbor, this thing, we just need to make sure that, actually when we are calculating this thing, we just need to make sure that it's not smaller than 0, or at least it's smaller than what? The number of boxes in at each level, how many, you have this many boxes at this level. So we just need to add these safeguards. Well, I'm going to print and confirm this if this is really working, because I want to make sure that okay, so now I'm going to print this to see if this is working. I'm going to print only for level 2, because I don't want to I don't want too many things to be printing on my screen. And I'm going to print ix2 0 and ix2 1. Okay? So this will show you what happens to the neighbors when my box is at 0. Oh, is there no... Okay, so what happens okay, now maybe this is not good because it's showing, yeah, it's not going into -1 because I've restricted it, but now it's showing the same number twice because I'm artificially sort of modifying the number. So what I actually need to do is to change these loop counters, or not, the beginning and end of the loops, to consider the corner case. Then it won't loop, so it won't create these duplicate numbers. So instead of doing it up here, we need to do it outside this IX and IY loop. So we need to make like the I min equals, so sometimes it's -1, but we want it to be so IY min also most of the time it can be -1, and the max can usually be 1, but sometimes we want this to be 0. And what is that case? It is when IX is 0, right? If this is 0, we want this to be 0. Similarly, if this is 0, we want this to be 0, not -1, because we can't go back any further. Also, similarly, we want, if these numbers are at the end of the domain, which can be calculated like this, then we want them to be basically that number. Okay, so maybe a more uniform way of writing this is to make everything say, if you are there, then okay. So now let's see what it outputs, because I think this will work, right? This will not loop over a duplicate. See, now you see that there aren't any, whoa, not good. Something didn't work, but now you see that, well, why is it doing this? IX is 0. If IX is 0, no, if IX is 0, it should not, oh, sorry, I forgot to do one critical thing. I have to change this to IX min and max. Yeah, of course it doesn't work if I don't do this. Okay, so now, so now it should work, right? See, no -1s, and no duplicate entries, because if this number doesn't become -1 if IX is 0, if it's at the corner, or if it's on this side. If IX 0 is 0, it means it's on this side. If IX 1 is 0, it means it's on the bottom side, so it uses 0. If this is at the other end, which is the large, in this case it should be like 3 or something. It's never larger than Why is it 2? Oh, sorry. Yeah, why is it? Is this okay? 0, 1, 2. There should be a 3 somewhere, no? I think there... If I equals 4, level 2, it should loop over... no? That's... There's something wrong with the loop here. I'm printing x2, which should be the neighbors. Ah, no, I'm looking at the parents' neighbors. I'm looking at the parents' neighbors. Yeah, this is the parents' neighbors. So it should be only 0 and 1. Two. Okay, I'm not sure what the... There shouldn't be any 2s. Because I'm looking at level 2, and I'm looking at the parent. So get IX should be returning only 0s and 1s. Maybe I can check if this is correct. So get IX should be returning... This should have only 0s and 1s. No, okay, that's correct. And so something went wrong here. Maybe my maximum value here is not being calculated correctly. IX no. This I think this should be 0, that's why. Okay, let's try again. Now I'm printing so this should return only 0s and 1s. Okay, good. So at the moment I'm only still at the parents' neighbors. I found the parents and I'm calculating its neighbors with this routine. I'm looping over all the, well, I handle the corner cases like this, and then I'm looping over all the neighbors, considering the corner cases. Now, I need to just loop over the children of these boxes. So this get index I see here is returning the index, which I can use to multiply by 4, and also loop over 4. So I need to loop in, am I using I somewhere? Yeah, I'm already using I. So maybe I can use J. Loop over 4 times. This is a loop over all the children. So by doing this is the index of the, yes.
After this, can we take a break?
Oh yeah, yeah. Okay. Yeah. So yeah, let's continue this tomorrow. So maybe we can have. Yeah, we're almost done with the M2L, so we're very close to finishing the FMM. But unfortunately, we ran out of time. So I will upload both this code and all the other ones, so that you can see what's actually happening inside the code. But this one, there might still be bugs because I haven't tested anything yet. So, but now you see how we calculate this part. This is the most complicated part. So, but we just used the neighbor finding. We did that first this morning. So it's easy for you to see how that neighbor finding is going to be used. So tomorrow we will finish this part and see if we can cover some more advanced tree topics tomorrow. Okay, so I think we will finish for today. And thank you. Okay.
Very concentrated.
Yeah, I ran out of time.
You have a great patience. So I think it's not easy to do the live.
Yeah, I think so. Yeah, it's becoming longer now.
Yeah. But you are so familiar with this.